everyone, it's Neil, and in this week's mini lecture, we'll be going over some more greedy algorithms. Just a disclaimer though, none of this content in this mini lecture is going to be covered on the midterm, so don't worry about cramming all this material in the next 3 days. But anyway, diving in, the first greedy algorithm we'll be going over is one that actually has really strong ties to real-world applications, and it's called Huffman encoding, right? And the motivation behind studying this is a lot of times in the real world, on almost a minute-to-minute basis, we're sending information to each other, right? For example, if I want to send some file, let's say it's like a textbook to a friend, right? What happens is that textbook as a file is compressed before I send it over. And the reason it's compressed is because we want the cost of sending a file over to someone else to be as low as possible, right? And so to do that, I compress the file, or my computer compresses the file as compactly as possible before sending it over, right? And so what that leads to is more efficient communication. And so one of the compression schemes we'll be covering is Huffman encoding, right? And essentially, we want to discover, or we want to use the most optimal compression scheme, right? And so, before diving into what exactly that means, let's take a look at a pretty basic example. Let's say we have, in our simplistic world, we have a textbook with only 4 characters, right? 4 alphabets, A, B, C, and D. And we want to compress this textbook and send it over to a friend, right? So the straightforward way to kind of translate these alphabets into bits would be, since there's 4 bits, we need log 4 number of bits for each alphabet, right? And so log 4 is 2 bits. And so we'll need 2 bits to represent each alphabet, right? And so I kind of arbitrarily assigned 00 to mean A, 01 to be B, etc., right? And so if we have a word that's A, C, D, D, B, we want to, encode it, what we'll do is we'll translate A to 00, here C to 10, and then et cetera, and we'll have our encoding for the original sequence of alphabets. And so that's kind of how these general, encoding schemes work. And so in particular, we have 2 goals that we want to accomplish, right? And the first goal is going to be, we want to preserve information. And essentially what this means is however we encode our original, alphabet, we want to be able to decode whatever encoding we have. And I'll get into an example of how that looks in just a second. But the second goal is we want to minimize the compressed size. And so what does that mean? It means that, again, the #1 goal of compression is we want to be able to compress our original sequence of alphabets or whatever as compactly as possible, right? We want to compress it and represent it in as few bits as we can. And so that's what the second goal is kind of talking about. And so another way of expressing the first goal, which is preserving information, is to say we need our encoding scheme to be uniquely decodable. And so here's an example that kind of walks through what that concept means. So let's say I arbitrarily chose, this encoding scheme, right? A translates to 0, B is 010, etc. And let's say I wanted to send over, AD to someone, right? So how that would be compressed, how I'd compress that is by saying A is 0 and then D is 10, right? I'm just following this encoding scheme. And so then I would send it over. So once, let's say my friend gets this, their task is to decode it, right? Decode it into the alphabet so they know what I originally wanted to send them. And so what they'll see is they'll see 010, and they could say, okay, 01 translates to C, and 0 translates to A. And so they'll decode it as CA, right? And so already here, you can see that what they're decoding is different from what I meant to send them. So yes, although 010 can decode into AD, because you can take, right, the first one, it could be A, and the second one can be D, it could also translate to CA. And in fact, 010 can also translate to B, right, if we see this. So as you can see, the 010, there's multiple ways that you can decode this sequence of bits, right? And therefore, there's like a lot of ambiguity to it. There's no one way to decode it. And so there's kind of like a loss of information, right? Whenever I send a sequence to someone else to decode, they'll never know what I truly meant because there's multiple ways of decoding it. And so that's what I mean when I say like we want to preserve information, our encoding scheme, we want to make sure that there's only one way to decode it. And what's a good way of guaranteeing that is through this concept called prefix codes. And prefix codes essentially, what it means is no alphabet encoding is a prefix of another one, right? If you see here, A's encoding, which is 0, it's not a prefix of anything else. B's encoding 10, it's not a prefix of anything else, and you can check that for all the other ones, right? And so prefix codes guarantee that a sequence of bits is uniquely decodable, right? So let's say we have, I don't know, 1, 0, 0, 0, and 1, 1, 0, right? There's only one way to decode this, right? The first two bits are going to be B. The second one can be an A. The third one can be an A, and these will translate into C. You can try it for yourself. There's no other way to decode this, right? It's uniquely decodable. There's no ambiguity left, right? So again, this kind of goes back into the first goal. Prefix codes achieve that. Now the second task is we want to minimize the compressed size. And diving into what that kind of means, let's say we have a book and let's say there's 4 alphabets in that book. And let's say in that book, A shows up 10% of the time, B shows up 20%, C 50%, and D shows up 20% of the time, right? And let's just say, kind of for example's sake, let's use this scheme to encode our alphabets, right? So how can I calculate kind of the expected number of bits that I need to translate one character? And to do that, you can just use concepts of expected values, right? A shows up 1/10 of the time, and we need 1 bit to translate A. So that's 1/10 times 1. B shows up 2/10 of the time, and we need 2 bits to translate it. And if we do this for C and D, we'll see that this leads to 2.6 bits per alphabet, right? So let's say my book is just arbitrarily 10,000 alphabets long. We'll need 26,000 bits to compress it and send that over. But that should raise a red flag already, right? Because if we see this original example, this very straightforward way of encoding it, encoding 4 alphabets was just using 2 bits per alphabet, right? But here, we need 2.6 bits per alphabet. And we're kind of like, this kind of using this, prefix, using this encoding scheme is going to lead to a large loss in efficiency, right? Even though 2.6 and 2 are, they may seem close. If you want to encode an entire textbook, 10,000 alphabets, the difference is going to be 26,000 alphabets using this inefficient scheme, 20,000 alphabets using the very straightforward way. And so that leads to 6,000 extra bits that we're sending, right? And so what leads to this discrepancy, And if you look into the distribution, how often an alphabet shows up, and you look at how we're encoding that, you'll be able to see what causes this inefficiency. C is the most popular alphabet, right? But in our encoding scheme, we're using 3 bits to decode it. Whereas A is our least popular, it's the least common alphabet that shows up, but we're using just 1 bit to encode it. Had we switched A's and C's encoding, so if we made A actually 110 and C B0, we'd already see an improvement in efficiency, right? So this kind of brings up the concept that the alphabets that pop up very frequently, we want to use as few bits as possible to encode those. We want to do more work on the alphabets that show up very rarely, right? And so that's kind of where the greediness of this entire algorithm, we'll see that with Huffman encoding. That's where the greedy algorithm part of it comes into play. We want to take the ones that are uh, uh, least popular and we want to give them the most bits. We want to kind of do that iteratively until we come up with encoding for everything. So again, kind of diving into how Huffman encoding works, it's a scheme that provides us the most efficient way to encode alphabets, right? So getting into it, this is kind of where the connection to 170 comes into play. The first step of Huffman encoding is to take the two least probable symbols. So in this case, they would be A and B, right? Then they correspond to the longest code words. What do I mean by that? What that means is we want to give the alphabets with the lowest probability of showing up, or the lowest common, the least common alphabets. We want to assign them the longest code words, right? Because once we take the expected value, that'll kind of optimize the expected value for the number of bits that we send per alphabet. And so, yeah, we want to take the two least probable symbols. They correspond to the longest code words having equal length, but they differ only in the last bit. We'll get into what that means in an example. And step two is we want to combine these two symbols into a super symbol and kind of repeat iteratively, right? And so I think the best way to understand Huffman encoding is through an example, right? So let's say in this example, A's probability of showing up, or A shows up like a quarter of the times, right? 25% of the times. B shows up also 25% of the time. And C, D, and E kind of show up less frequently. So, essentially running Huffman encoding on this algorithm, we see that, we greedily start by analyzing the two symbols with the lowest frequency, right? And in this case, it's going to be D and E, right? They both have just 15% of showing up. And what we do is we kind of as the algorithm states, we combine these into a super symbol. Let's call that DE. We're just combining them, now treating it as like a combined thing. And we sum up the frequencies. So now it's going to be 0.15 plus 0.15 is going to be 0.3. And then this kind of last thing, they correspond to the longest code words and differ only in the last bit. So just kind of arbitrarily, we want to, we're coming up with an encoding for D and E. We only have there's only two symbols, so we can just use one bit for each symbol, right? So we can let 0 correspond to D and 1 correspond to E for now. And then now what do? We kind of repeat, right, on the smaller size alphabet. Now our alphabets are A, B, C, and DE, DE being one super symbol. And so now we go to the two next lowest frequency alphabets, right? In that case, it's going to be 0.25 and 0.2, right? B and C. We do the same thing here. We combine these two into a super symbol, BC, which has a frequency of 0.45, right? 0.25 plus 0.2. And then again, we do the same procedure. We assign 0 to B and 1 to C. And again, the top bits, I'm kind of, associating them with zeros, and the bottom bits, I'm associating them with 1, right? Whenever I combine stuff. So yeah, so that's kind of the second procedure, and keep going, right? The next two lowest frequencies is going to be, I think, 0.25A and 0.3, which is DE. And so we can kind of combine those two up here. Sorry. We can combine those two. And that'll give us ADE. Or actually, let me do this. I'm going to draw that up here. It's going to be ADE with frequency 0.25 plus 0.30. It's going to be 0.55. Right, and again, we assign a 0 here and A1, let me just write that here, right? And so now, let me make this entire diagram smaller. Oops. Now we kind of, continue this process one more time, because there's two remaining alphabets, right? A, D, E, and B, C. Both of them are super symbols. So then we combine these, bring these in together. And this thing is going to be A, B, C, D, E, since it covers like all of the alphabets now. Again, this last step, we're combining ADE and BC. And so their frequencies are going to be 0.55 plus 0.45, which is 1.0, which means we've kind of covered all of the distributions. And again, we assign 0 up here and 1 down here. Now we have this entire, tree, right? So essentially, once we've kind of constructed out this tree, we go backwards to come up with the actual encodings for each alphabet, right? So for example, let me use a dotted line. So if we want to come up with what the encoding for A is, we start here and we go backwards and follow A, right? So if we go backwards, we'll see that first we hit this 0, and then we hit this 0. So A's encoding is going to be 0, 0. Now to do B, we'll do we'll kind of go do the same procedure, right? For B, we kind of follow this line up into here, right? And so as you see, for B, we first hit this 1, and then we hit this 0. So B's encoding is going to be 1, 0. For C, if you follow the tree down, you'll see you hit this 1, and then you hit this 1. So it'll be 1, 1. For D, you hit this 1 up here, now, and then you hit this 1, and then you hit this 0. So D is going to be 1, 1, 0. Actually, sorry about that. Made a minor mistake. So for D, actually, you follow ADE, right? So the first alphabet that you hit is 0. The next alphabet, so again, just to make it extra clear, you kind of follow this tree, and then you go down and follow into here, right? So the first digit that you hit is 0, and then you hit this 1, and then you hit this 0. So D is going to be 0, 1, 0. And if you follow the same tree down for E, you'll get 0, 1, 1. And as you can confirm, none of the, all of these encodings, none of them are prefixes of each other, which means we've achieved prefix code, right? So Huffman encoding gives us these prefix codes that also minimizes the expected value for the number of bits we need for each symbol. And so kind of analyzing that, taking the expected value again, we see for A, it shows up 0.25 or 25% of the time. And the number of bits that we need to represent A is 2. And then for B, it'll be, 0.25 times 2. And if we continue this for A, B, C, and D, we'll see that the expected value is 2.3 bits per alphabet, right? 2.3 bits per alphabet to, to encode 5 alphabets, right? A, B, C, D, and E. But the traditional, if we look at the straightforward way of doing it, kind of like the same thing we did here, A, B, C, and D, we did log 4 and got 2 bits per each symbol, right? So if we did that here, we'd see log is 2 of 5, and we take the ceiling. So traditionally, if we approach it using the straightforward way of doing things, we'd need 3 bits per alphabet, right? Since there's 5 alphabets, log 5 and sealing it, we'd see 3 bits per alphabet. So we see 2.3 is significantly better than 3, right? Again, they might seem like pretty close numbers, but if you want to encode an entire textbook or a huge file, let's say a million alphabets, right? This difference in 0.7 bits per alphabet is going to yield incredible, huge improvements in efficiency, right? And so again, the key concepts of Huffman encoding lie in greediness, right? At each step, you're choosing the ones with the lowest frequency, and kind of combining them and kind of iteratively going through that, and then going backwards once you constructed the entire Huffman encoding tree to come up with the actual symbols. And so, yeah, that's kind of a overview of Huffman encoding. Lily is going to cover another greedy algorithm next.
Hey everyone, we'll be covering Hornsat and Horn formulas in this segment. I'm assuming most people will be watching this after the midterm, so I hope the midterm went really well for everybody. Regardless of what happens, it's time to move on to the next topic, and this is one of the last topics we'll be covering for greedy algorithms, so I hope this will be an interesting mini lecture. I found this really exciting when I was in 170 because Hornsat is one of, the most complex problems that we know of a polynomial time algorithm for. So yeah, I hope this is interesting and I hope you learned something new today. So Hornsat and Horn formulas and SAT problems in general, if you're familiar with those, are all just ways that a computer can reason about logic. And the way we do this is through Boolean variables and clauses that connect those Boolean variables. So let's dive in and see what Boolean variables are all about. So a Boolean variable is exactly what it sounds like. It is a variable that holds a Boolean value. So say x. We can write x is either true or false, and we can write its negation, x bar, or also read as not x. Basically what happens is if x is true, then bar x is false. If x is false, then not x is true. To connect these Boolean variables, like these are sort of our statements that are true or false, we want to string them together in a humanly reasonable way, just like perhaps we're conversing about if this is true, then something else is true. Or when I think about Hornsat formulas, I always think about those weird online riddles that you do about, Alice and Bob are talking about Carl, and Alice said Carl stole the cookie at 8 a.m., but Carl said he was in outside at 8 a.m., but then Bob says, one of Carl and Alice is lying, stuff like that. It's very sort of complicated, and you want to just have a consistent way of writing things so that your computer can understand what you're trying to reason about. So the way you do this is through clauses. And there are two kinds of clauses in Hornsat, or Horn formulas. One of them is called implications. Implications is sort of exactly what it sounds like. It's some statement implies some other statement. And on the left, we have a bunch of and operators connecting some positive literals. So you can have x or y, x, y, w, but you can't have stuff like x bar. You have to have positive literals. Positive literals. And on the right hand, you also need positive literals. So for example, I can write z, but I can't write z bar. Again, positive literal. So what this means is if x and y and w are all true, then z must be true. On the other hand, I have pure negative clauses. You might be guessing that it has a lot of negations, and you would be completely correct. It's a bunch of negative variables connected with ors. So maybe I have not x, not y, not z, not w. What this means is not all of these can be true. So you can't have x, y, z, w all be true, then this would not be satisfied. All right. So here it's all negative literals. So you might be noticing something very interesting about these two kinds of clauses. They sort of pull us in different directions. On the one hand, implications seem to want us to assign things to true. It encourages us true behavior. So it encourages us to assign whatever is on the right side to true so that we can satisfy these implications. But on the other hand, these pure negative clauses encourage us to assign things to false because we want the negation to be true, which means the literals themselves, the variables themselves, have to be false. So these two sorts of clauses are yanking our string in different directions. And so the ultimate question is this: is there a satisfying assignment? So what is a satisfying assignment? A satisfying assignment just means, is there a way that I can assign true or false to all of my Boolean variables on this list, I don't know, x, y, z, w, or any others that you would want to add. I want to assign Boolean values to these things such that all of these clauses are satisfied. So this seems like, I don't know, it seems like a pretty hard task, right? You have all sorts of implications, and you can put as many things as you want on the left side, and you can have as many negative clauses as you want. But ultimately, we need an algorithm that returns for us a satisfying assignment when there is one, and tell us that there isn't one when there isn't. So in the next part of the video, we'll see how to construct an algorithm using the greedy approach. Or I don't know, the book uses the stingy approach. All right, see you then. Let's look at the algorithm for Hornsat. This algorithm returns a satisfying assignment if there is one, and returns that there are no satisfying assignments if there is none. So let's look at the algorithm. It starts out with assigning everything to be false. So all of our literals will be assigned to false. And then you go through the list of implications and only set things to true if we have to, which just means that, if stuff, for implications, if stuff on the left is true, then we must set the right side to true. We're sort of forced to do this. There's no getting out of it. All right. So let's see. And then after this step, after all of these are done, you return the assignments. If they still satisfy the pure negative clauses, otherwise return impossible. Okay. So what this means is when we first set everything to false, we automatically satisfy all the pure negative clauses because, well, all of them are negative, and you satisfy every single one of them because all of them are false. However, they're not guaranteed to satisfy the implications, which is why we need to loop through the implications and see if there's anything that requires us to set some of the positive literals to true. For example, if on the left side, all of these, if I evaluate this left side to be true, then I better set the right side to be true. We're forced to do this. There's no choice. So let's look at an example. Suppose I have a clause, or I suppose I have a number of clauses that look like this. W and Y and Z implies X, X and Z implies W, X implies Y, and then I have just implies X, and I have negative Z. Okay, so this is a Hornsat problem because, as you see, we only have implications and pure negative clauses. So the first thing we notice is this guy right here. This guy is called a singleton. What this means is you basically have to set X to be true. So at first, of course, we set X, Y, Z, W to all be false. And by this, we have to set it to true. This basically means like true implies X. So X is forced to be true. And now we see X implies Y, so Y is forced to be true. All right, we see nothing else is forced, right? Because X and Z is not true because Z is not true. W, this is also not true, so we don't care about these. So now we're done with all the implications, and we look at the last one. We look at the negation. And not Z, well, Z is false, so not Z is true. So now this assignment right here will, in fact, satisfy all of these conditions. So we just return this. So this is pretty straightforward. It's very clear to see that in order to sketch a proof of correctness, in order to sketch a proof of correctness, I'm doing a very bad job of writing here. I hope you can read this. For proof of correctness, we can first say that, every assignment that we change, we're forced to, right? So if we end up, if this algorithm terminates, then that must mean that we've already gone through all the implications, checked that they're satisfied. And we also have checked that they satisfy the pure negative clauses as well. So they must satisfy everything. So if the algorithm terminates, then if the algorithm terminates and the pure negatives are satisfied, then we do have a satisfying assignment. On the other hand, if we no longer satisfy the pure negatives, it means that we don't have any satisfying assignment, because again, we were forced to change stuff to true when we actually change them. We're sort of stingy that way. We don't change them just because we want to. We're forced to because of these implications. So what this means is, you know, basically we're done with the proof of correctness. There's a bit of, I don't know, there's a more rigorous way of saying this, but this is the intuition that since we're forced to change things to true when we do change them, it means that if we return anything, it's correct, and if we're not able to return that, then no satisfying assignment exists. And that's the gist of Horn set.